Application of trig to help take down the castle. Hey, I'm going to do a quick problem with an application of trig. It's one of those problems that I remember back in 1980 something. I attended governor school at St. Andrew's Presbyterian College. I think that was Governor School East here in North Carolina. And I remember a problem similar to this. I mean, holy cow, this has been on my mind for over 30 years. And I could never do this problem back in the day. And it's a very typical application of trig problem. And you've seen this in some shape, form, or fashion if you studied any trig whatsoever. I would hope you would have, but let me show you what happens. There's this big fortress right here, and a bunch of bad guys. If it's Lord of the Rings, it's orcs. I don't know, if it's Army of Darkness, it's King Henry and his men, and little skeleton warriors. Regardless, what happens is a little spy from another camp comes up, and it's nighttime, and he's down there on the ground, and what he does is he looks up to the very top of that wall, because he wants to know how tall that wall is. The height of that wall kind of gives you, hey, that wall is 40 feet high, 50 feet high, 100 feet high, 300 feet high. Maybe we might have to devise which weapon can actually hit it. We can practice it over there to make sure our weapons can lob into it at that height. So when we go into the real battle, we're not just, making it up as we go, So what he does is he looks up there and he sees the angle of elevation is maybe 4 degrees from the horizontal looking up. That's the angle of elevation. Now, if you are the bad guy looking straight across, your angle of depression would be 4 degrees. So there would be those alternate interior angles when two lines are parallel. They'd be congruent. So he realizes that's all he's got. So what he'll do is, maybe he's really good at estimating distance, and it's nighttime, so he walks up 100 feet from where he took that initial angle of elevation, and he gets another angle of elevation up there just like that to the same point, and maybe this time it is 15 degrees. Whoops. Yeah, there we go. 15 degrees from the horizontal looking up. So that's what he's got. You're saying now, how could he do that? Well, there's a lot of instruments that do it. One easy instrument to do that with is just take a protractor and glue a little straw on the end of it so you can look through it. Tie yourself a little fishing wire and a little weight down there at it, so that way you could stand there and take it and kind of look up and it'll move. That's a cute little way. I mean, that's pretty cool. So I used to do that back in the day, do little tricks like that and so forth. So he gets away, runs off. So they said, okay, what you got? He goes, well, I've got a 15-degree angle of elevation there. I've got this 100 feet here, and I've got that. And it seems like we really don't have that much. All we know is that this is a right angle here, so we have one right triangle there. So there's our right triangle. That's 15 degrees. The other acute angle in that right triangle obviously would be complementary. So that would be, 75 degrees. So all three of them add together to equal 180. And we're trying to find out what the height of that wall is, x. But that's all we got are the three angles of that triangle. And since all 15, 75, 90-degree triangles in the universe are similar to each other, they all have the same shape, but they could differ in size. So what we need to do is say, well, we need to find out what one length is, and this side right here happens to coincide with this triangle. So this is going to be, we'll let that be y. And we don't need to find out what this side length is. We need to find out what y is, this length right here, because that's the one side that corresponds to both triangles. But looking at this triangle, we have 4 degrees, let's see, 15 degrees there. This is which means that angle right there beside it that forms that linear pair is going to be 165, so they both add together to equal 180. Well, if that's 165 and that's 4 degrees, that's 169 degrees, which will give that as 11 degrees. So let me just draw that triangle out of there. So there's 11 degrees, there's 165 degrees, there's 4 degrees, and we have that side length of 100 feet. And what we want to do is find out what this one is, y. It is not a right triangle. So therefore, you can forget your some old hippie called another hippie tripping on apples. Those are the definitions of those three basic trigonometric ratios as they pertain to a right triangle. So when you're dealing with an oblique triangle, a non-right triangle, the first thing that pops in my head is the law of sines and the law of cosines automatically. And looking at this bad boy, we see that we have this 11 degrees and this 100 feet. So that is definitely, this is an angle side angle case. Some of you are like, oh, ambiguous case, angle side. Well, I've already got all three angles of the triangle, so it's there. So let's use the law of sines. It's a non-right triangle, law of sines. Once I found out what y is and put it here, then I can use my some old hippie called another hippie tripping on apples to determine that. So I don't need to use a law of sines or law of cosines, though I could, but why would you in a right triangle? So does this make sense? Rewind the video and watch it again. Took a shot there, 4 degrees angle of elevation, got closer, now it's 15-degree angle of elevation. So let's see how tall that wall really is. So the law of sine says the sine of 11 degrees is to 100 as the sine of 4 degrees is to y. So if I cross multiply, this is 100 times the sine of 4 degrees equals y times the sine of 11 degrees. So y would simply be equal to the 100 times the sine of 4 degrees divided by the sine of 11 degrees. Now, fortunately, I have my handy-dandy TI-84 calculator. I'm checking to make sure my calculator is in degree mode. And I'm going to type in 100 times the sine of 4 degrees, press enter. Then I'm going to divide that by the sine of 11 degrees. And I happen to get 36.56 feet in this case. That equals y. So this kind of looks scary now that you start thinking about it. So if that is y, I can come over here and replace this with 36.56 feet. And then I can say, hey, can I use, there's one that I'm not going to use, and he's tangent. I have the hypotenuse, hence that is sine or cosine. Some old hippie called another hippie hypotenuse. I could use the sine of 15 degrees is equal to opposite over the hypotenuse. Or I could use the cosine of 75 degrees is equal to adjacent over the hypotenuse. So either one of these will work. So I'm going to multiply both sides by that denominator on the right-hand side and get 36.56 times the sine of 15 degrees is equal to x. So whichever one of these I do, I'm going to get the same answer. 36.56 times the sine of 15 degrees. And holy schmoly, that wall happens to be only about 9.5 feet tall. That's all it is. Only about 9.5 feet tall. So in other words, he's got a pretty good idea. So maybe he was just a little hobbit or something like that. It's a very short wall. Maybe he shouldn't be panicked about it. Now here's the thing. What happens if we had come over and this 15-degree angle of elevation had only creeped up to maybe 6 degrees? How much of a difference would that have made? Well, I'm anxious to find out. So that's 6 degrees. That would have changed this to 174 degrees, which would have made that a 2-degree angle. So let's very quickly find out what would have happened in this scenario. So I'm changing everything right now real quick. So I'm changing this. This is all going away. So this is now only 6 degrees, which makes this 174. That dropped down to only 2 degrees. And that's still 100 feet. So this is now the sine of, let's be a little careful here, the sine of 2 degrees is to 100 as the sine of 4 degrees is to y. And let's see what happens very quickly. When I solve for y, I'm going to simply take 100 times the sine of 4 and divide that bad boy by the sine of 2 degrees, and I get approximately 200 feet, just like that. Wow, that made a big difference. So when I come over here and put that, so now what I've got right here, and I've got to be a little careful now, this is no longer 15 and 75, this is now 6 degrees, this is 84 degrees, so now this is the sine of 6 degrees is equal to x over 200, so let's see what happens. This is 200 times the sine of 6, and the wall is still only about 20.9 feet tall. It's still pretty tall, but it didn't change it that much, did it? That angle of elevation right there. It's an interesting little problem. I recommend you play with these problems that combine multiple triangles. Dealing with oblique ones, you got to use that law of sines or law of cosines, find that common side, transfer to that right triangle, and use the sum of hippie, call another hippie, tripping on apples, not acid.